Okay, yeah, 13. Hope you've all had a brilliant Christmas and New Year and are ready now to tackle some of the toughest stuff that we're going to do. As promised, this video, I'm sorry it's a little bit late, but you will see that I've had my hands full. And as promised, this is Nancy. Say hello. Good girl. So after that excitement, we can get on with the video. So we are, like I said, talking about fatigue and the recovery process. I want to show you this video clip to start. What you're seeing is footage from the British rowing team ahead of the Olympics in 2004, and that's Matthew Pinsent, James Cracknell, and on the end is Steve Redgrave, and they are taking part in a competition, a training event. What I want you to see is the situation that Steve Redgrave gets himself into. You see he's still rowing, and over the course of the next few lessons we're going to talk about how the body gets to that state and what happens afterwards. So, as we move on, you'll see we're talking about the recovery process. And basically, as you'll see there on the screen, we're talking about things that happen after you, as a performer, have completed exercise. And we're going to think about that in two ways. So, during exercise, so you can maintain your performance. For example, if you're doing a sprint during a team game. So, if I'm a footballer, just done a sprint, how I recover from that sprint to be able to participate and continue to participate in the game. And then also after exercise, when we're thinking about recovery for our next performance, next competition, whatever that may be. Main aim of recovery process is to take the body back to its pre-exercise state. You need to remember that terminology. All right, how do we go restore the body to its pre-exercise state? And we're going to think about the removal of byproducts and the replenishment of fuel. They're the two kind of key elements of things: the removal of byproducts, replenishment of fuel. Okay, what I want you to do while we're doing this is just keep thinking about energy systems, and that's an exam question that we haven't used. It's actually from a different exam board, but you get the basic premise. Yeah, so you can pause that, have a look at that, but keep thinking about energy systems when we're going through these bits of work. So, thinking about that image, those athletes after an event, I'm going to talk to you about something called EPOC. Alright, and EPOC is excessive post-exercise oxygen consumption. Okay? So you'll sometimes see it as excessive, you'll sometimes hear it as excess. Excess post-exercise oxygen consumption. Basically, the amount of oxygen you consume in excess after exercise. Now let's just look at this graph, right, and I'll talk you through it. And again, this would be a really useful screen grab for you to get, so that you've got this in your notes to save for drawing it out in lesson. So think about this is just at rest. All right, so this period here is just a normal period of time. We're at rest. Oxygen consumption's up the vertical axis here, and then we've got time along the horizontal axis. So we start exercise here. You'll notice that our oxygen consumption goes up in a curve. Alright, our oxygen consumption can't, if I get my words out, can't go immediately up, because if you think about our respiratory processes, we can't go from zero breaths, or our resting rate of breaths, to our maximum respiratory rate instantly. That's a process that takes time. But because of that, because it goes in a curve, so this is how it affects our respiratory rate going up, the amount of oxygen that we're consuming going up, it leaves us with this oxygen deficit. So if oxygen had been available, we would have been using it here. So we've got a deficit. Alright, now think about that, think about what energy systems and such will be going on there, but this is a deficit. It means that oxygen wasn't available here, but if had it been, we would have been using it. Alright, so this is where we get to our maximal oxygen consumption, and thinking about VO2, it means with the volume of oxygen that we're using. So we've got this nice curve, then we've got a plateau to the point where we end exercise. Now you need to look at how this graph comes down, alright, because we've got the slow component here to the end of our recovery, which is 1 or 2 hours, and we've got the fast component here, the fast stage. Alright, so the fast stage here is alactic acid, or lactic acid, and the slow stage down here is the lactic acid or lactic acid stage. Alright, fast stage, slow stage. Now what we're going to talk about is specifically what happens in those two stages. So if I just advance this presentation on, you'll see that term there, oxygen deficit, is mentioned, and there's just some good terminology there for you. Yeah, if we can't provide enough oxygen for a task, this is known as oxygen deficit, which is what causes our breathing rate to increase until we can meet that demand. So this is where the EPOC comes into it. Alright, it's a recovery process to go back to our normal state. And again, down here we're talking about the two phases. Fast phase. So this is where we're going to think about what happens in each phase. Alright, so in our lactic acid's first fast component, really crucially, we replenish the phosphagen stores to resynthesize ATP and PC. If you think back to those systems and you remember that ATP cannot be resynthesized until exercise drops below maximum. You remember that. The minute that happens, or even the second that happens, we begin to start resynthesizing ATP and PC, so we get that phosphagen stores back. It takes us approximately 3 minutes to fully restore that ATP, and 50% of our recoveries happen within 30 seconds and 75% within the first minute. Right, and then you're going to hear the process requires approximately 3 to 4 litres of oxygen. If you think about it, when you've been exercising, you've been for a run, you've been doing whatever, afterwards, how long you breathe harder for than when you've stopped exercising, and this is what's happening. Okay, think about where we've seen the term myoglobin before, where myoglobin is found in the muscles and what myoglobin does. Now, when ATP is generated aerobically within the muscle, that happens through oxymyoglobin. So muscle stores of myoglobin with O2, we get there the stores of oxymyoglobin. And if you think about oxyhemoglobin, where we know that is the blood carrying red blood cells, the oxygen carrying red blood cells, oxymyoglobin, very similar principle in that these are the myoglobin within the muscle that transport oxygen. Alright, although these obviously don't go into the blood system. Don't confuse myoglobin and hemoglobin. So we'll move that on, and we'll look now at the slow component, and this is where we're talking primarily about lactic acid being removed from the body. And rather than thinking about removed, if we more think about converted to. So we know that lactic acid is converted with pyruvic acid. When it goes into Krebs cycle, that's all of our aerobic energy system stuff. It can also be converted to glucose, and it can also be converted to proteins, and we'll talk about those things in a little bit more detail in lesson. But you'll see there that this requires a greater amount of oxygen. So we're now talking 5 to 8 litres, and this is a far longer process, between an hour and 24 hours, and that is dependent upon the intensity of the exercise and an equivalent, basically how much lactic acid we have got stored in that has been created in our muscles because of the intensity and the duration of that exercise. One thing that also happens, you'll be aware of, is that we remove carbon dioxide. So we know carbon dioxide is formed as a waste product, and it has to be removed, and it is removed by within the plasma of the blood. Basically, as you can see there, it forms a carbonic acid, and this terminology here, which is something you probably won't be quite well, in fact you definitely won't be quite for your exam, but it's just good knowledge for you. Basically we form a product called carbaminohemoglobin, which is what carries carbon dioxide within the blood. This is taken to the lungs and expired, it's breathed out. What we've got is a scenario where chemoreceptors detect elevated levels of carbon dioxide. They will, within the blood, the elevated levels of carbon dioxide that the blood carrying is detected by chemoreceptors within those blood cells, within those blood vessels, and triggers the body then to increase the respiratory rate. It was one of the ways that our respiratory rate increases. It will also is one of the processes by which the body continues to breathe elevated respiratory rate because of the elevated level of carbon dioxide. And you can see here, really importantly, cardiac output and respiratory rate remain higher during recovery to expel carbon dioxide from the lungs. Okay, cardiac output, as we know, is the amount of blood being pumped out of the body, out of the heart per minute, and the respiratory rate, again, number of breaths that we are taking per minute, higher during recovery to get rid of that carbon dioxide out of the lungs. So that is a bit of a whistle-stop tour, to be honest with you. Year 13. We're going to talk about EPOC in detail in lesson on Tuesday. Apologies, I haven't given you a huge amount of time to watch this video, but as you saw at the start, I had my hands full, being pretty busy, but I'll catch up with you about it all on Tuesday. Alright, cheers.